Well, it is my pleasure to welcome officially Jos Uffink, who's a professor of philosophy at the University of Minnesota. He works in the philosophy of physics, philosophy of science, and history of physics. As we will see today, he's done his PhD in theoretical physics at the University of Utrecht, where he's been for quite a number of years in the Faculty of Science in the Foundations and History of Science department. He's now in the Department of Philosophy at the University of Minnesota. He has published many articles, way too many to single anyone out. He works primarily in the foundations of quantum mechanics and statistical physics, I think it's fair to say.
Yes. And
has written a number of very important reference works, for instance in the Stanford Encyclopedia, in the Handbook for the Philosophy of Physics, and similar things, and has several ongoing projects right now, one of which is Schrödinger's role in the foundations of the history of quantum mechanics, and also in the history of statistical physics and thermodynamics, as we will hear tomorrow. Today he will be talking about Schrödinger and the prehistory of the EPR argument. Please, Jos.
Thank you very much, and thanks for inviting me, and thank you for coming here, listen to me. So yes, this work, I should mention in start, is grown out of joint work that I did with Christoph Lehner in Berlin, who was great help in deciphering works of Schrödinger, especially his handwritten notes that are unpublished but are still online from his Nachlass in Vienna. And I do want to talk especially about Schrödinger's role, which I think has been underappreciated in the development of the Einstein-Podolski-Rosen argument. So let me try to give an overview of the main points I want to raise today. Of course, just background knowledge. In March 1935, Einstein, Podolski and Rosen published their famous paper, a 4-page paper in the Physical Review, in which they famously argued that quantum mechanics was incomplete. It has the title, "Is the quantum mechanical description of reality complete?" They made this point by means of an argument which included what we would today call an entangled wave function. And this EPR paper played a decisive role in focusing the debate on the interpretation of quantum mechanics in subsequent years, and now is also seen as more or less a landmark paper that cannot be ignored if you want to study, for example, works in quantum information or quantum computation, because this is really the source, or at least the first, the first time that entanglement came to the foreground in the discussions on the meaning of quantum mechanics. Actually, of course, the EPR paper doesn't contain the word entanglement. It was only coined in the subsequent months, when Schrödinger responded to the appearance of the EPR paper by publishing 2, maybe 3 papers in a very short period, in which he elaborated decisively on the EPR paper, and he introduced the term entanglement, or Verschränkung in the German original, and famously claimed that this was the essential difference between classical conceptions of physics and quantum theory, and also the famous cat paradox. Now, it's a more or less common viewpoint amongst present-day historians of physics that Schrödinger's papers, in response to the EPR paper, were more or less triggered by the EPR paper. And there's obvious reasons for that, because in one of the first papers of this series, he says that he was inspired to publish all of that by the EPR paper. And especially Arthur Fine's book, The Shaky Game, from the 1980s, is, I think, mainly responsible for this common viewpoint, where he analyzes the papers by Schrödinger from this period and sort of tries to trace all of the ingredients of that paper one-to-one to the correspondence he's having at the same time with Einstein during the summer of 1935, and basically argues like, oh, Einstein is writing this to Schrödinger, and look, later on we see this appearing in Schrödinger's papers, as if Schrödinger was more or less guided by this input from Einstein in writing all these papers. I think, and I will argue, that this is a quite unfair view of the history, and it overlooks more or less that Schrödinger and other people have been worrying about entanglement already since 1926. And moreover, what I think is completely unknown to this day is that Schrödinger already had in his unpublished writings all of the essentials of the EPR argument 4 years before Einstein, Podolski and Rosen published it. So that's the main message I want to bring across today. And well, don't hesitate to ask any questions if there's anything unclear at this point or later. So let me jump ahead. And first thing, I will more or less presume that the EPR argument is familiar to all of you. And if not, just tell me or let me, I will be happy to remind you of what the argument is about, if you want. But if it's unnecessary, then I'll just continue. The common conception, or the commonest view in the historiography of the EPR argument, is that this is an argument that sort of grew out of the photon box argument that Einstein presented earlier in the Solvay conference of 1930. And maybe you're not as familiar with the photon box argument. I will come back to it later, but basically it's a thought experiment that Einstein presented there, where he has a box that contains photons, as well as some clock mechanism that will operate a shutter and operate it for a very brief time. And the argument he presents at the Solvay conference is this: suppose you weight the box before setting it in operation, then the clockwork mechanism operates and releases a photon, and then afterwards you have, well, as I tried to point out, in Einstein's original intention, the idea is after it has operated, you could either weigh it again and then find out how much mass energy is missing from the box due to the escaped photon, and then predict what the energy of the photon is going to be even while it's far away. Or you could open the box, inspect the clock mechanism, find out exactly when it opened the shutter, and then make a prediction about the time of arrival of the photon. So you can either predict the energy of the photon if you do one type of measurement on the box, or you can predict the time of arrival of the photon if you do another measurement on the box. And the photon is just far away, presumably it doesn't know or doesn't care about which experiment we do on the photon box, and that's more or less the problem, because energy and time are in some sense complementary. It's not quite clear how Einstein argued in the original presentation, because we don't have any written record of that. We actually only have Bohr's version of how he understood the argument, later from 1948. And yeah.
Sorry, just to very quickly, surely the point must have been to say that you could know of that photon the time and the energy at the same time. So there couldn't be an uncertainty,
yes,
which of course would contradict the quantum mechanics of today, or what the others, people believe there, right? What the other physicists believe at the Solvay conference.
Yes. I'll accept your summary. But the way Bohr presents in his famous paper on discussions with Einstein, he recounts the Solvay conferences, and every time Einstein presents a thought experiment, Bohr interprets it as if Einstein tries to find a counterexample to the uncertainty relations. Right? And so in Bohr's reconstruction, he sort of resolves the whole paradox here by trying to point out that if you weigh the box, then you have to put it in a gravitational field, and then he argues that the precision of the weight measurement is somehow related to the momentum of the box, and so for very precise weighing you have to control that momentum to an extraordinary amount. That would mean, according to the uncertainty principle for the box, that the position of the box is uncertain, but that means you don't know its height in a gravitational field. And then by a famous application of the redshift, the gravitational redshift formula, you would also not be able to control the rate of the clock mechanism. And so you wouldn't be able to predict the time of arrival. And so it looks like Einstein's argument is defeated by applying the same uncertainty relation, this time for the box, as he was trying to defeat for the photon, showing the consistency of quantum mechanics. But we do know from 1931 that Einstein visited Ehrenfest at the time, and when he left Ehrenfest, he immediately wrote to Bohr and says, "I've talked to Einstein and you completely misunderstand his intentions. He never intended the photon box as an argument against uncertainty relations. Instead, he's certainly convinced of the consistency of the uncertainty relations, but he says you always still have a choice. You can either measure the box, reweigh the box, and thereby predict the energy, or you can open the box and inspect the clock mechanism and predict the time of arrival. Now you can do both at the same time. That's what he admits. But there's still a choice we can do on what measurement we perform on the box. And depending on what choice we make a different prediction on the photon, which is far away and presumably has properties independent of what we do to the box. So this letter from Ehrenfest, written very soon after 1930, shows us that Einstein already intended the photon box more or less in the same way as the EPR argument reasoning is concerned. So definitely this is a sort of precursor of the EPR argument. But, and this is more or less central for what I want to talk about, the photon box argument has many loose ends and complications that make it so complicated and so many distractions here that people have not been. It's hard to see through all of these embellishments and see at the heart of the problem that came to the foreground in the EPR argument. So first of all, the photon box arguments is about measurements of either time or energy. And this raises the question of whether time is really a bona fide observable in quantum mechanics at all. And I'm not sure how familiar you are with that problem, but there is a huge literature on the problem of whether time could be represented, say, by a self-adjoint operator in Hilbert space. The answer is it depends. Depends a lot on what you mean by time, or which time. The question is, even if there is such an observable, is there an uncertainty relation for those two quantities? That is also a very involved question. Then the next complication is that by weighing the box in a gravitational field and employing the result of that to infer something about energy, that Einstein is relying on the equivalence principle of GR. Now that invites many questions into whether Einstein is secretly presupposing GR, or whether Bohr was entitled to involve the redshift formula from GR in his reply. And much of these discussions can actually be led to a clear and consistent conclusion. And I'm not saying this is as difficult it is today as it was at the time. But if you go back, if you compare that to the EPR paper, where you only have just two particles described by plain old non-relativistic quantum mechanics. There's no problems about its consistency with gravitation or GR at all. And you are only considered in measuring position or momentum, which is also no doubt about their status as observables. All of these distractions, I would say, go away. What is perhaps even more important to me is that in the photon box experiment, as well as in earlier thought experiments that Einstein talked about, there are only discussions about uncertainties. Einstein never even proposed a wave function to describe the situation in his thought experiments. Neither does Bohr, in his reply, ever use a quantum wave function to describe the situation. As such, the argument could never have led to a discovery of entanglement, because if you don't have wave functions, you can't even formulate the formula of entanglement. So the EPR paper sort of stands out in contrast to the photon box argument because it explicitly introduces this entangled two-particle wave function, and because there's only a question of choice between either measuring one or the other of two observables on one system and using the correlation in the integral to make a prediction about the other particle, which might be very far away. What else is known about the prehistory of Einstein's part of the EPR argument? That is that in 1932, in another letter from Ehrenfest, he's being asked if he couldn't reformulate the photon box argument into what he calls wave mechanical terms, which I presume also simply also means non-relativistic terms. So getting rid of all these references to the equivalence principle and interline. And in his response, Einstein presents a version in which he now talks mainly about a collision of a photon with a mirror. That's actually also not quite non-relativistic wave mechanics because it refers to photons, but it's at least a much simpler conceptual setup. And some historians have seen this as a sort of main stage in Einstein's development en route to the EPR paper in its full glory in 1935.
And that's in a letter to Ehrenfest?
Yes.
Okay.
There's a previous letter from Ehrenfest to... actually, I'm not sure if it's a letter. I think it's the setting at the time is Einstein is about to board a ship in Rotterdam to the US, and Ehrenfest visits him in Rotterdam, and on the next day Einstein writes to Ehrenfest about his visit the previous day. Okay, so this is known, but I want to point out that Schrödinger was puzzling about entanglement much earlier than all of this. This is from a letter that he wrote. There were a couple of letters he wrote to Kramers and to Jos and also to Bohr, roughly about the same within 2 weeks or so, in November 1926. They all have a sort of very similar problem. The letter to Kramers is, I think, the shortest and the clearest of these three. And translating from the German, he says here, if we join two mechanical systems together in thought without actual interaction, then its eigenfunctions are the products of the eigenfunctions of the single systems. But when we superpose these products with arbitrary coefficients under the single condition that the sum of their squares is equal to 1, then this aggregate cannot be written as a product of the aggregates referring to the single system. This contradicts my interpretation of the wave function, because in that case the state of the combined system must be provided by the states of the single system. I'm not quite sure if it's clear what he's talking about here, but if you want to or see that in more modern terminology, if you have a state of a composite system, so this is a small psi, this is a capital psi. This is the state of a joint system, and if the systems don't interact, ordinarily you would assume, oh, there's a state of the first subsystem and there's a state of the second subsystem. But each of these states can actually be in superpositions of different eigenfunctions. So if these are the eigenfunctions of one system and these are the other eigenfunctions of the second system, now if you in order to still be a product state, it would have to look like this. So this is but if you take general superpositions of those eigenfunctions, you would get something like this. Under the condition that this is 1, as Schrödinger notes, for the coefficients. But in general, this is not equal to that. It only is equal to that if it happens to be the case that those arbitrary coefficients factorize in this form. But that is very far from the general situation. So if that's not the case, then you can't write the joint system, the joint state, the state of the joint system as a product of states of the two individual subsystems, which contradicts his interpretation of quantum mechanics, because in that case the state of the combined system must always be provided by the states of the single subsystem.
Meaning in that case, by interpretation.
Yes.
Yeah.
Now, the very fact that states of composite systems in general do not factor in the states of the component systems, that is the phenomenon of entanglement. So it doesn't have a name at this time, but Schrödinger is certainly very much aware of this problem, especially as a problem against his own wave mechanical interpretation of quantum mechanics. He writes, as I said, it's very similar in his other letters and in his letter to Bohr, where he incidentally mentions something he says, high respect of Bohr. So he says, this must all be known to you perhaps for a long time, but he also writes, I am at this moment more confused about the foundations than ever. That's a wonderful state to be in when one is about to travel to America to spread the wisdom that one doesn't possess to an astonished public. Because as he is about to go on a trip to lecture on wave mechanics. He also says clearly at this time that he thinks that the statistical interpretation which was proposed by Bohr in June 26 does not suffer from this problem because these things only have a statistical meaning for Bohr. Incidentally, let me also mention that although he says, he writes about, oh, this must have been familiar to you for a very long time, but in his reply, Bohr is completely silent about this. He doesn't confirm this at all. In my interpretation, that means Bohr was not at all aware of these, of entanglement at the time. Now, I will sort of briefly skip over the next period, because although, yes, initially Einstein thought entanglement was a big problem for his own interpretation of wave mechanics, but not so much for the statistical interpretation. A few years later, that interpretation had sort of emerged into a more developed framework by contributions by Bohr and Heisenberg and Pauli and von Neumann into what we now call the orthodox Copenhagen interpretation, in which the statistical interpretation is part and parcel. But in this more mature Copenhagen interpretation, now Einstein, as Bohr, also becomes critical of that, and in the end, he sort of recognizes that entanglement is going to be a problem for that interpretation just as well. But as I said, I will mainly skip that period in favor of focusing on his writings in 1931. And here is the clearest example of what I mean. It's in a letter to Sommerfeld from 1931, and I will quote extensively from that. He writes, "The foundations question torments me more and more, and unfortunately completely fruitlessly. May I babble a bit to you? Mag ik de bedankt hier etwas voorschetsen? We have been debating for hours in the seminar about the following actually quite simple case, take one dimension. There's a mirror and there's a photon which impinges on the mirror. On a heavy mirror, we measure its momentum very precisely, and the answer is 0. Simultaneously, we measure the position of the photon very precisely. The color of the photon and the position of the mirror are therefore very uncertain. Then I let the photon reflect on the mirror. It thereby absorbs twice the momentum of the photon. After this has happened and the photon is a good distance away, I have a choice of measurements on the mirror. Either determine its position or the color of the photon. Namely, if I measure the position of the mirror, its value will, for a sufficiently heavy mirror, be the same as the position on which the collision occurred, and enable a very precise inference about the position of the photon, whose initial position was unknown. But when I decide to measure the momentum of the mirror, abstaining from its position, then I can, because its initial momentum was known, determine the color of the photon. Admittedly, I cannot learn both the position and color of the photon simultaneously. but I can learn without interfering with the photon, either one or the other, whichever I please. And what I hope you recognize, this is the exact same strategy as employed in the EPR.
So is it, how does it relate to the specific version of 32 or so, when Einstein talks to Ernefest in Rotterdam? Because it sounds like a mirror and a photon too. And
yes.
So it may be the same thing.
It may be the same thing, and that was 1932, right?
Right.
Yeah, so
right after that.
Yes,
So.
and I would argue that this is, that Einstein also learned this from Schrödinger, or at least discussions in 1931. But the argument by Einstein is actually not that elaborate, and certainly not that crystal clear as Schrödinger's theory. He continues, even more amazingly, our mirror is what he calls a universal instrument for the position and the color of the photon in the following sense. When the photon is treated in the way above, both the position and the velocity of the photon leave a trail on this instrument, and both will be registered with accuracies whose products fall far below the limit of Planck's constant. Both of those trails really exist because it depends on the decision of my free will to use one or the other, although then the second one is washed out. Because the photon has nothing to do with the manipulations on the mirror, one can hardly say that its sharp position or sharp momentum is only created by one of those manipulations. In any case, this is not a creation in a real, but at best in a mental sense. One would like to conclude that a photon always possesses a definite position and momentum, a view that we have long ago abandoned as paradoxical. The only way out, it seems, is by something like an emergency degree in quantum mechanics. Statements about what is real about the object are forbidden. They deal only with the relation object-subject, and apparently in a much more restrictive sense than in any other description of nature. So this is Schrödinger dabbling to Sommerfeld. Actually, Sommerfeld's response is also completely bland. He says that he put the letter to Hans Beek, his assistant at the time, and the only comment Beek makes that correctly, in the sense that is that Schrödinger uses the word color and velocity and momentum of the photon more or less indistinguishably, whereas actually velocity is always the velocity of light, and momentum is something different. And so he's a bit sloppy in here. But they have nothing further to say about the whole issue. Even though, as I said, this is very similar already to the EPR paper, because we have a pair of systems, they've interacted in some sense, and they've since been spatially separated. We consider a choice of measuring one or the other of two non-commuting observables on the mirror, allowing an accurate prediction of one or another of comparable observables on the other system. There's a recognition that we cannot actually do both at the same time, but these predictions must nevertheless correspond to some physical reality, because it depends on our free choice whether we will do one or the other of two measurements, and we never have to touch or interfere with the photon at the same time. The only things that I think are still missing are that, well, not the only two things in which it differs from the EPR paper is there's no reference to completeness, which was the main conclusion that the EPR paper points to, and of course there is still not any mention of a wave function, and therefore also not of entanglement here. But it's pretty impressive as it stands. Now, you may recall that Schrödinger refers to a seminar where all of this sort of came out of. And you might ask yourself, what seminar is he talking about? Well, it's actually not all that hard to determine that seminar, although it took me quite a while. This is from the chemical journal who diligently published summaries of all the colloquia and seminars sort of going on, especially in Berlin. And so here you see November 4, 1931, Berlin. There is a colloquium by Albert Einstein entitled Über die Unbestimmtheitsregelung. And what you can see from this summary is he talked once again about the photon box experiment. So there is man stelle sich ein Kasten mit einem automatisch öffnenden und schließenden Klapper vor, der außerdem mit einem Uhr versehen ist. Beim Öffnen der Klapper soll aus dem Kasten ein monochromatischer Lichtstrahl austreten und in einer bekannten Entfernung viele Lichtjahre aufgestellte Spiegel reflektiert werden und dann zum Beobachtungsort zurückkommen. I assume you are familiar with German? No. Not too much? Okay, so anyway, so there's a box that contains radiation, there's an automatic shutter that's being it's connected with a clockwork. It opens the shutter for a very brief while, and then there's a quantity of light that is being emitted, and this time it's being sent to a mirror that is being that has been positioned many light years away, and then comes back to the observational.
Is that the full text of the colloquium report?
That's a summary.
Okay, but that's what the only thing we have.
It's the only thing we have. Yeah, and it's not written by Einstein probably, but by somebody who was in the audience. But that's the way that this chemical journal operated. We had summaries of all the talks that were going on, at least the main ones. There's some other stuff at the end where he also talks about work with Tolman, which is sometimes called the Einstein-Tolman, Rosen or ETR paper. I won't go into that because it's sort of a sidetrack. But what we do know is that Schrödinger attended this talk because here are his notes. It's called Bohr-Einstein Beispiel, or Bohr-Einstein example. And I won't read all of this, but here you will see a box with a clock and a shutter, and it's suspended in a weighing scale. So this is supposed to be weighed. Then this is the path of the photon. Here is a mirror, and above the mirror it says Sirius, the star Sirius, so indeed many light years away. And then it comes back here, sent to a prism and be observed. Now, first of all, the inclusion of the mirror was not present at the Solvay conference. But in Einstein's argument, I think it only is added for rhetorical reasons, because it allows him to contemplate the idea that, well, the photon escapes, it goes very far away, we can wait for years, make up our minds whether we want to reweigh the box or we want to open it and inspect the clock mechanism. And perhaps if we want to make an extremely accurate measurement, as is needed in those arguments, maybe one would object that that costs a lot of time. Well, by taking this enormous amount of time, many, many years, we would have all the time we needed to perform an experiment as delicately as we like, and we have all the time to make up our minds of which choice we make, all the while the photon is traveling. So it has a certain rhetorical quality, the arguments to include that mirror, but for the essentials it's rather superfluous. The second thing I wanted to note about Schrödinger's commentary here is that, maybe surprisingly, you can see that Schrödinger was not convinced by Einstein at all. Because on the second page of this two-page manuscript, you see that he doubts the argument, and precisely because he is arguing that it's inconsistent to assume that there was a clock mechanism that could open a shutter in an extremely short time and still assume that the energy of the system is very well known. And incidentally, there are he talks about discussions with Wigner at the time, and there are formulations of the energy-time uncertainty relations that would preclude that, because you know, of course, that in an energy eigenstate, the system must also be stationary, so it doesn't have any evolution in time at all, non-trivial evolution. And if you want to have a system that behaves one way at one time and in an other way at another time, which are very short apart, very close to each other, then there must also be a considerable spread in energy. So he doubts Einstein's conclusion about the photon box experiment for that reason, and that's because this is still about energy, time, and uncertainties. But there's more. Here is another short manuscript, undated, but it contains the Spiegel-Lichtquant example that we also see in this letter to Sommerfeld. And this is in a folder which is called the Szilard mirror measurement, or Szilard Spiegelmessung, and it's dated 1931.
But why is Szilard?
What is Szilard?
Why Szilard? I mean, what does he have to do with
We'll come back to that.
Okay.
It's just, well, you'll see in a moment, at least the name of Szilard. This is just what I found. But the fact that this is the same experiment as he writes to Sommerfeld made me curious. And you will see here a discussion of uncertainties and uncertainty relations at various times. And it ends actually rather without any clear conclusion, but it does end with a question where he said, well, this is the way it goes for light, how about particles? And that, I think, suggests to me that now he wants to talk about just plain non-relativistic quantum mechanics or wave mechanics without any appeal to relativity. And that's where this next manuscript comes in. And this is much more interesting, and it's also dated, and as you can see here, it's 4th of November 1931, but below the 4, if you look closely, there's a 5. That was the original date. So anyway, this is very briefly after the Einstein colloquium in Berlin. And here he writes, his handwriting is terrible, that's why Christoph was such a great help. Es handelt sich folgende: Gestern vom Szilard im Kolloquium aufgeworfene Frage. There's Szilard. Zwei Systemen, S und S', wurden getrennt. Ist es möglich, durch eine S auszuführende Messung, je nachdem man sie möchte, entweder die eine oder die andere von zwei konjugierten Realen, A' or B', of System S' in folgender Weise scharf zu machen, dass die Produkte der beiden Unschärfe kleiner ist als H. Planck's constant. That's the question Schrödinger poses. And then there are several Fourier or initial considerations here and there. And this is I think a 10-page manuscript, so I'm not going to continue. But this is extremely interesting because, well, here's an English translation of the problem which he attributes to Szilard. Two systems are separated. Is it possible by an appropriate choice of measurement on system S to make one or the other of two conjugate variables, A' or B', of the other system sharp in the sense that the product of their unsharpnesses is less than Planck's constant? And if we translate this problem into quantum mechanics and in wave mechanics, and then I will assume the Dirac notation, or Schrödinger doesn't use that, of course, but it's so familiar nowadays. The question becomes simply this: there's one given state or wave function of the total system, and the question is, can you decompose it in such a way that these are the eigenstates of quantity C, these are the eigenstates of quantity D, such that if you find, say, an outcome Cn of the first system, can you then make a definite inference to quantity either A' of the second system or a quantity B' if you made a measurement of D instead? Is this clear? So basically the question is, mathematically speaking, can you have two different bi-orthogonal decompositions of a wave function? Now what's interesting is here that Schrödinger initially conjectures that the answer to this question is no. And he starts to prove that by various attempts. And one attempt fails, and then he tries another approach, and then that approach fails, and then he tries another approach, and then that becomes too complicated anyway. And then halfway through the manuscript, he suddenly realizes, well, my conjecture that the answer is no might be wrong. And he ends this rather dramatically. He says, Schluss, finished, the end, and the statement is simply wrong, underlined 3 times. And from that point in the manuscript, we see him trying to establish the converse conjecture, that the answer is yes. And that happens very soon, because then he comes up with this wave function, and this is his original notation. And there's a joint wave function for the 2 systems, and this wave function is, as is easy to see, an eigenfunction of the total momentum, sum of the momenta of the 2 particles, and at the same time it's almost an exact eigenfunction of the difference in positions, at least when this function alpha of k is sort of brought and only slowly varying. So, for this wave function, for a system, a joint system in this particular state, if you were to measure its momentum on one subsystem, you can completely predict the momentum of the other subsystem, because it's a joint eigenfunction of these 2 momenta. If, on the other hand, you were to measure the position of the first subsystem, then you can almost exactly predict the position of the second subsystem. So that shows that the answer to his problem is yes. You can do it in such a way that the product of the unsharpness is way below the usual uncertainty relations. And this wave function that Schrödinger comes up with in November 1931 is, I would say, equivalent to the wave function used by the EPR problem. Under a trivial choice of the reference frame, so you have to put k0 equal to 0, and you would have to put alpha k equal to 1, which Schrödinger didn't do because he was more careful about normalizability of wave functions than EPR, who didn't threw all the mathematical considerations in the wind in the EPR paper. So this is actually my main find, that Schrödinger here develops also the wave function for the entangled 2-particle system, equivalent to the one later used in the EPR paper. Actually, you can also find more from this period. There's another document where you see him actually working out the Schmidt bioethanol decomposition theorem to ask himself how general this phenomenon is, that one joint wave function can have multiple bioethanol decompositions. And he finds out, well, this was of course known to the mathematicians by Schmidt, 1909, if I'm not mistaken, but it was unknown to the physicist, and sort of Schrödinger sort of worked it out for himself. And I presume that this interest in the bioethanol decompositions in 1931 must have been triggered by also this paper. Okay, so let me try to, well, give you my reconstruction of what went on in this period. It's clear that Einstein gave this seminar in November 1931, and it raised a lot of interest and discussion in the audience. And remember, there was a mirror in his way he set up the experiment. And what I guess is that maybe Szilard asked a question about whether the interaction of the photon with the mirror, recoil, might have raised some additional source of uncertainty, and that some question like that, and then from that point on, the discussion centered not so much on the photon box, with which it all started, but just the collision of the photon with the mirror, which also is the start of Schrödinger's work. But the very next day, he boiled down the entire argument to a consideration in non-relativistic wave mechanics, just considering two particles with position and momentum, never having to talk about energy and time at all. And since, as I said, they were colleagues at the time, they must, I'm sure Schrödinger must have talked to Einstein about his insights here, although because they were talking at the time, there was no written evidence of that. So what we do know is that, as I said, after the EPR paper finally appeared, Schrödinger and Einstein started corresponding again, this time Einstein in the US and Schrödinger in Oxford. And Schrödinger writes in his first letter, "I was very happy that in the paper that just appeared in the Physical Review, you have publicly caught the dogmatic quantum mechanics by its tailcoats about that which we discussed so much in Berlin." And in his next reply, he points out once again, "You have pointed out these things years ago in Berlin, and we discussed them so much with hot hat in the seminars." So there was repeated references by Schrödinger about these discussions in Berlin about what I take to be the very content of the EPR paper. And of course, previous historians have read the same letters also and seen the same references to discussions, but I guess they never have thought or conjectured that these might have been so much technical, detailed discussions and not just about conceptual issues about about the foundations of quantum mechanics, but the very heart of the entangled wave functions and the EPR argument. Also, it's interesting is that although Schrödinger was very happy about the appearance of the paper, he also gave some mild criticism to Einstein because of the lack of mathematical sophistication, and he says that he would have liked to see more detail in the paper, and that it gives Einstein a tutorial about the Schmidt decomposition theorem, and said that actually, well, and there's actually another document here in the folder called Exercises, which contains his notes for the letter to Einstein, where he's actually much more critical. He says, "From the mere fact that by measuring one or another of two quantities on one system, we are stuck with wave functions that represent incompatible properties of the other system, we cannot construct a trap." Actually, this should be a noose for quantum mechanics. We only obtain a contradiction when we presuppose a bi-orthogonal expansion or decomposition. So Schrödinger at the time is adamant that the whole issue is depends on the existence of multiple bi-orthogonal decompositions. Einstein doesn't care about bi-orthogonal decompositions at all, and that's what he says in his response. He says, "Das ist mir wurscht," or "I couldn't care less."
So does Schrödinger by 1935 know Schmidt's decomposition theorem and call
I
it
doubt
that?
it.
He
No.
just states it basically because he's worked it out for himself.
Yes.
Okay.
No, I think he doesn't even call the bi-orthogonal decomposition theorem. but that's what it is. And actually, in the papers he published in '35, there's one popular paper in the Naturwissenschaften, and there's a second, more technical paper in the Cambridge Philosophical Society transactions or proceedings, which also contains a proof of the biochemical decomposition theorem. Here are my main conclusions. There's no doubt that the EPR argument actually was emerged somehow from the photon box experiment. I will not disagree at all with any historian who presents that viewpoint. But in sort of timeline between that event and the 1935 paper, there is an important role that Schrödinger played in boiling it down from the photon box argument with its many bells and embellishments and distracting complications to the sort of lean and clean version that you find in the EPR paper, and therefore for the role of entanglement, because now it contains a wave function in which you can recognize entanglement. That, as we can see, Schrödinger found that argument in November 1931, and we see it reappear in Einstein's paper in 1935. And I think Schrödinger ought to be recognized for that particular role in fathering the EPR paper. And maybe we should call it the EPR Schrödinger argument, something like that. That's the main conclusions I wanted to draw. So, thank you for your
Okay, so let's open the floor for discussion and for questions.
Yeah.
Who would like to go first? I have a quick question maybe to start. Toward just I think the slide before this one, you say that in Einstein's letter, or response here, he dismissed by orthogonal expansion, and then went on to talk about incompleteness in a way different from the EPR paper. So I would also be interested in that. Even though I understand this is tangential to your hypothesis here, I think it's still interesting.
Yes, absolutely. And it's something that many historians have commented upon, like Don Howard and Arthur Fine and Christoph also. I've got another paper which deals with that more deeply, but well, thanks for asking that. Actually, let me first say that the way the EPR paper actually argues for incompleteness is somewhat implicit. They don't actually complete the argument that would establish that. But the way they argue, or let me first give a sort of overview. Completeness or incompleteness in this context is about the relationship between two kinds of objects, two kinds of entities, which you might consider, and one kind is that of the, let's take the terminology that Einstein in his letters approaches. So suppose we are realists and we assume that physical systems are in some real state of affairs or real states. And that's something that belongs to that system and it's there regardless of whether we know it. And then there are theoretical descriptions. Which in the case of quantum theory would be wave functions or quantum states. And the question is, what kind of relationship is there between these two realms? And so this mapping might be, say, but one option is that there's a one-to-one mapping. That is to say, for every real state of affairs, there's one unique theoretical description, and for every single theoretical description, there is one real state of affairs. So, in mathematical terms, that would mean there's a bijection of these two domains. In the Einstein letter from Einstein from 1935, this is what he calls completeness. So in his letter to Schrödinger he says, if there is a one-to-one correspondence between these two, then I will speak of completeness. This means that incompleteness is any failure of this mapping to be one-to-one. How might a mapping fail to be one-to-one? And so these are the alternatives. So let me see. So there might be real states without theoretical description. Or, this is not necessarily disjunctive, but there might be two or more real states with the same theoretical description. Or there might be two or more theoretical descriptions corresponding to the same real state. Or finally, if you want to be complete in a discussion of incompleteness, there might
could be theoretical descriptions without real states.
Theoretical descriptions without a real state. Now, this last option is not very interesting for all of this. But In the EPR argument, as I understand it, the argument goes that, well, you could make a measurement of position on one system, thereby make a precise prediction of the, say, the momentum of the second particle. There's this criterion of reality which says, if you can precisely predict something for this second system, there must be an element of reality there. And this language of elements of reality means, in my view at least, or can be translated, in my view at least, to say that momentum must be a real property, it must belong to the real state of the system. If you were to make another measurement on the first subsystem, you can also make a definite prediction of its position. That also has to be a real property of that system. So if you say that the state of that second system should not depend on what you do to the first system, it should have both position and momentum.
Yes, real.
Yeah, they're both real. Well, there is no wave function in quantum mechanics that's both an eigenstate of position and momentum. That means we are in this situation. There are real states of affairs for that second subsystem that do not have a wave function description at all. So I think this is what EPR can do.
So you could say that the version of completeness that Einstein uses in this letter to Schrödinger is a more general one than the one used in
Yes,
EPR.
but there's more I wanted to say about it. If you look at how he now argues for the incompleteness of quantum mechanics, he uses an entirely different argument. And he, as I said, he says, I don't care about bioorthogonal decompositions. What he simply says is that, well, let me give you a discussion for it. It's this conclusion. How does that go? Well, he says I have a joint wave function for the two systems, and I don't care if it's bioorthogonal or not, but let me say it's something like this, where now I'm not supposing that either of these two collections of wave functions are orthogonal or complete or whatsoever, except this one. This one is eigenstates of an observable. So if, let me use it. So I can measure A on the first subsystem, and then depending on what outcome I obtain, I infer that the second system must be in state C and phi n. Let me so I find if I find outcome an, then this is the state of the second system. Or I can measure B and then, well, I can use the corresponding description, won't bother, but now there is some so if you like, after it, these are the relative states of the second system, given in this case an outcome of this alternative measurement.
So these would be two theoretical descriptions.
Yeah, so now Einstein argues this second system doesn't care about what measurement I do, so they should refer to the same state, but there are different wave functions, so I have several wave functions for the same real state. This, of course, is not one-to-one, therefore it's a failure of completeness, therefore quantum mechanics is incomplete. But the way there is a failure of a one-to-one correspondence is because of this, which later in an earlier paper he focused especially on those two situations. And this one he calls, later calls incompleteness, and this is what he calls overcompleteness. For Einstein, in any case, it's a failure of one-to-one correspondence, but for Einstein, this is, in the letter, this is the crucial conclusion, and this is what the whole thing boils down to. Now, problem, question, is overcompleteness quite as dramatic as Einstein would make it? Overcompleteness is actually quite well known in physics. It happens every time in gauge theories, where you have multiple theoretical descriptions for the same physical situations, and in many other cases as well. So for Einstein, this is the thing to point at, but it's not, at least not clear to me, that this is so worrisome as one might initially think.
Yeah, so I think incompleteness of the form 2 or 3 are more worrisome.
Yeah, yes. And this one is more or less uninteresting. These are the two interesting parts, where you would say, well, there's really something that this theory lacks.
Yeah.
In this case, you would say, oh, the theory has more expressive power than it need to be, but that's not a source of worry.
Well, it might be, because you might worry that you have some you're really describing descriptive fluff about the real physics you don't get at the real degrees of freedom, the sort of concerns that you might have with gauge theories. But these are different concerns than with...
Yes, and in a sense, I think any theory has some descriptive fluff. Sometimes you're more successful to get rid of it than other occasions, but I do admit, of course, that there is a difference here in that in gauge theories you can usually sort of nicely get to a sort of get to this descriptive fluff sort of leads to an equivalence relationship, and then you can hopefully sort of divide out the equivalence classes, and then you get a more condensed view and say, okay, well, that's the real stuff, in which I sort of take equivalence classes over all different gauge variables. This is not possible in this case, because this doesn't give rise to an equivalence relationship. But I was rather shocked to find that Einstein only points out to this conclusion in his letter, and perhaps even more that many of the historians regard this as especially hard to find. You think that, oh, the EPR paper is actually a sort of adulterated version of Einstein's pure thought, because that's actually been written by Podolski. And here is Einstein in his own words, so this is what he always had in mind. And Presumably, therefore, this is the expression of pure genius, and Podolski's work is sort of a lesser status. And I would rather be inclined to take the opposite viewpoint, that it might be true that it's written by Podolsky, but the viewpoint expressed there is much more to the point, much more sharp than it is in Einstein's own letters.
But a question on that, it goes again beyond a little bit about what you talk about, but Arthur Fine points out that really EPR do a little bit more than they would actually have to establish their conclusion of incompleteness. And Einstein later cleans up that argument, not in a 1935 letter to Schrödinger, but if you go, I think, into the 1940s, there are cleaner expressions of the problem from Einstein.
But they always go back to this.
They always do? Okay.
Yeah.
Okay.
So this is indeed the start of a fairly consistent way in which Einstein presented the issue. So yeah, there's a maybe subtle but important difference between. So Einstein also says to Schrödinger in the beginning. I didn't quote all of that, but Schrödinger says, "Oh, I was so pleased about the work that you wrote with in the Physical Review," and Einstein writes back and said, "I was actually quite disappointed with the way it came out, and Podolsky sort of smothered it in erudition, but he wrote it because of the English the language, and then he says, I would have put the whole thing in quite different terms." So he sort of, put some distance between himself and the EPR paper. Disowns it.
I have more questions, but I would like to give you guys an opportunity to jump in.
So my reservoir intelligent question is empty, so there's no stupid ones.
Oh, there are no stupid questions, there are only stupid answers.
Well, my question was, one learns from the popular literature at some point in the 1940s, Einstein and Schrödinger were bickering with each other about claims of priority.
There were what?
They were disputing about priority, about maybe more like 25 theories that don't work or something like this. So they were challenging each other priority on some work. My question was, well, if you think that Schrödinger was first on some of the main ideas of EPR, why didn't he dispute the publicly dispute the priority? I was first.
Yeah, well, there are two things to say about this. First of all, in other letters that I saw Schrödinger write also to other people, I did not recognize him as somebody who generally cared much about priority issues. Second thing I should note maybe is that in this period, and certainly in earlier years, this is also generally true. People didn't always refer to other people. It was true by Einstein. Sometimes didn't refer to people he should have recognized in today's standards. Another thing is that, of course, Schrödinger himself never published anything about this. He never also published anything about his criticisms on quantum theory in general. There are notes that I found from 1929 when he made notes for a lecture criticizing quantum mechanics, and then it turns out he never gave that lecture, or at least gave that lecture but on a completely different subject. Schrödinger was certainly hesitant to speak out against the orthodox viewpoint of quantum mechanics, although he disagreed in private. Another thing which distinguished the two is that for Einstein the issues seemed to be rather easy. There's a paradox that you get in the EPR paper if you assume quantum mechanics is complete. The alternative viewpoint that Einstein favored is, well, if you just assume that quantum mechanics is not a complete description of nature, then the problem disappears. And then we could all be happy. Schrödinger never believed that. He believed that the viewpoint that quantum mechanics is incomplete in Einstein's sense would also not work, and he points that out to Einstein also in his correspondence, saying das geht nicht. Which means that for Schrödinger did not have any positive alternative to come up with. For Schrödinger there was a problem, but he didn't see a solution. Or at least he didn't consistently believe in one particular solution. There are many passages in his papers. Sometimes he says things like, oh, this might be due to the fact that our present understanding of quantum mechanics is non-relativistic, and maybe if we get to a future more satisfactory version of quantum field theory, then the problem will disappear. Or maybe it's the case that the entanglement will somehow fail for distances beyond the that are spatially separated. And that somehow this is all an artifact of the non-relativistic quantum mechanics, and that it might disappear in a better relativistic theory. There are also cases where he seems to be looking at the different approaches, and so, for example, if I look at the
here he says the emergency decree is the way.
Yeah, the emergency decree is the way, which I think is basically saying we should give up on realism. Quantum mechanics is not about what is real, but it's merely about object-subject relations. So that might be the way out. So he sort of changes his mind all through the years about what might be the way out. And the upshot is he doesn't have a clear single solution to the problem. I think that really stopped him from going public with his worries. And Einstein didn't have those worries because he said, well, I think the answer is just quantum mechanics is incomplete. So in a sense, Einstein was more brave than Schrödinger. Was he annoyed that Einstein never mentions his name? Maybe you can read some of that in his repeated mention of, we discussed all this so much in Berlin, you remember well, Einstein? I'm not quite sure. I actually didn't know that in the 40s or 50s they got into debates about priority. I would be very pleased if you could send me some references to that. but because then I would have to rethink my conception of him as not being too someone who didn't care too much about getting all his priority claims recognized. So that was not a stupid question at all.
Good. We have to try to ask a stupid one, but
Sure.
Yeah.
it's just basic understanding. So the first photon box experiment, right, was so this thing was relativistic, based on ontology of particles, and the observables in game were time and energy.
Yes.
And then we switched to a more mature experiment where it's non-relativistic with an ontology of waves, and it's between momentum and position. And all of that were kind of addressing issues with the first experiment using some ends. So that part is right?
Well, it's thanks for that question. I did talk about wave mechanics because that is the usual name given to the theory that Schrödinger developed in 1926. To contrast it with matrix mechanics, but it's more it doesn't necessarily refer to ontology. Yes, originally Schrödinger thought that the waves in his wave mechanics refer to something real. But as we also seen, he gave that up very shortly after. It's more, it refers to a certain methodology. You represent systems by what is known as a wave function. But that system can, ontologically speaking, very well be a particle. So you've got a particle, and you can describe it by a wave function. That's not to say that the particle is the wave function, or that the wave function is the particle. It's a certain description you apply to the particle.
So this is this new methodology that allows, because sometimes you said that the notion of entanglement was tied to the notion of wave.
The notion of what?
Of entanglement? Entanglement?
Entanglement, yeah.
You said that it was tied to the new experiment being formulated in terms of waves. So what I was...
Yeah, but that doesn't refer to the ontology. There's one use of my vocabulary that might be confusing to you. Perhaps I should have said quantum states all the way instead of talking about wave functions. But I have adapted myself to try to avoid speaking this way because one of the issues that I didn't talk about, but that also was emerging in Einstein-Schrödinger correspondence, is that Einstein thinks that Schrödinger's wave functions are states and therefore have a ontological significance. Schrödinger has to point out to him, say, no, that's not the way I understand wave functions at all. They do not refer to, they're not one-to-one descriptions of states at all. And he says, well, states should be referred to as real states of affairs, description of what the world is like. a wave function is not necessarily a description of what the world is like. It's a theoretical description of the world. But there's not a one-to-one map between them. So it's highly misleading to speak of, especially for Schrödinger's point of view, to talk about wave functions as states. But the common vocabulary, of course, in physics is that when I talk of wave functions, people talk of quantum states. Now you might say, oh, there's a difference between quantum states and classical states. But if I describe a system by a quantum state, and which quantum state that is, that might ultimately be very dependent on what kind of measurements you perform on another system, which doesn't interact with that system at all. So, in a sense, the experimenter has a choice of what quantum state you ascribe to that system. And that's another issue that Schrödinger develops in the next year, and it's now called steering. By making particular choices, you can attribute almost any wave function you like to a system just by your own choice. It's not necessarily something that's a property of that system. But it's still part of the apparatus of quantum mechanics that you have a physical system and you describe it by some quantum state, at least some vector in a Hilbert space, whatever name you would give. But the question, what does that ontologically represent? Does it commit you to a wave ontology or a particle ontology, or do you, that's a completely different issue.
I'm afraid we should stop. We're really already 20 minutes almost beyond the allotted time.
Okay.
So please join me in thanking Jos once again.